Hello everyone, and welcome back to another demonstration section of mine. And in today's video we would be learning one more aspect of protein structure visualization, in which our main focus today will be to learn how do you manipulate more than one model. So far so good, we were working on a single model. Well, now it might happen in your molecular modeling career or in your project work that you might want to deal with more than one model at once. So we would learn what are few tips and tricks that are very handy when it comes to a situation when you have to manipulate more than one models. Okay, and specifically in this demonstration I will teach you as to how do you detect the conformational changes in the given molecule. Okay, so in this practical, we will compare two different conformational states of the same protein, the deoxy and oxy form of hemoglobin. Okay, so let us begin our practical demonstration. Okay, so of course we would be using our deep view, our own very good and my favorite molecular structure visualization program. Okay, so as usual, before we start out anything, let us set all the preferences to default so that it would be easier for everyone to follow. Okay, in case you have made any changes in your previous working sessions. Okay, so what we are supposed to do in this practical is to compare the oxy and deoxy conformations of hemoglobin and see as to what things happen when oxygen goes and binds to your hemoglobin. Okay, so now in order to compare the two conformations, well, you would have to first align the two structures. Okay, and when you want to align the two structures, all you want to do is you want to superimpose the two structures. So the first task that we would need to do in this practical is to superimpose the structure of hemoglobin, or you can say the structure of oxyhemoglobin, on that of deoxyhemoglobin. Okay, and your deep view allows superimposing either all of the two molecules, or you can start out with small part of your two models that you want to superimpose. Okay, and deep view also allows you to color the model to emphasize what are the conformational differences that you might observe. Okay, we are going to deal with all those aspects in this practical. Okay, so first let us begin by loading the model with PDB-ID 1HHO. Okay, so I have already downloaded these models from PDB. So if you don't have these models, you can use this PDB identifier and download those models from PDB website. Okay, so I have already done it, and you, I hope, remember that how do we download the PDB files as such. Okay, so first I have loaded this model with PDB ID 1HHO.pdb. Okay, and this 1HHO.pdb is the alpha, contains alpha and beta subunit of oxyhemoglobin. So this 1HHO model is the one which is bound to oxygen. Then we have got another model with PDB ID 3HHB. Well, let us load that as well. Okay, so this model 3HHB corresponds to the alpha and beta subunit of deoxyhemoglobin. So 3HHB is the one, is the conformational state of your hemoglobin to which oxygen is not attached. Therefore, we call it as deoxyhemoglobin. Okay, so first we will learn how do we carry out the simple superimposition of hemes in the beta subunit. Okay, so now in order to examine conformational changes that accompany the binding of oxygen to hemoglobin. Okay, so this is what we are going to do. So what we will do is that we will try to first superimpose the hemes that are present in the beta subunit of oxyhemoglobin and deoxyhemoglobin, and then examine what are the conformational changes that happens when your oxygen goes and binds to the heme portion of your hemoglobin. Okay, so now since we have loaded these two proteins, or you can say we have loaded the two conformational state of the same protein, what we can do is that we can press this zoom center so that both the models would uh, come in the center of our screen, right? So after pressing this zoom center, and before we compare them by superimposing, well, now I think it is important for you that I tell you some tricks that becomes very handy when you try to handle multiple model. Okay, so there are some features in your deep view or SPDBV that are very important to learn when you try to handle multiple models. Okay, so one of the most important feature is that you can use this another window called as layer infos. So you can go to Windows and select this layer infos window to activate it. Okay, here you see this is called as the layer info window. Okay, so this layer info that correspond to the layer information window, it provides a very convenient control of multiple models. Okay, if there are multiple models, as you can see, you can control these multiple models that you have loaded very conveniently using this layer infos window. Okay, so now what we need to do in our practical, for this purpose I need to adjust my layer info window in such a way that I could see the layer info windows as well as the 3D representation of my protein molecule simultaneously. Okay, so here is what we have. We have layer info window placed just below the graphics window of your SPDBV. Okay, so now what I will do, I would color by layer. Okay, if I color by layer, what deep view does is that it colors the two model in yellow and blue color. Okay, so by default the first model that you load would be colored as yellow, and the second model that you have loaded would be colored by blue. Okay, if more than one model are present, if we'll say for example if more than two models are present, your deep view would assign more colors as per the availability of model. So since we have since we are dealing with only two models, the first model that it has loaded, it has been colored in yellow, and the second model that you have loaded has been colored in blue. Okay, so now let us click on this control panel to activate it, and I will show you there are some more features over here. Okay, so this particular portion in your control panel usually tells you as to what model has been loaded. Okay, so do you see, and if you click on this 1HHO, okay, a menu appears, as you can see over here. A menu appears that shows the names of all the loaded model. Okay, and in deep view, when you try to load more than one model, we call them as layer. So this one HHO is the first model that you have loaded, so this is what we call it as layer 1, and the next model that you have loaded 3HHB, that would be your layer 2. So in deep view we consider them as layers. Different model would be termed as layers in SPDBV. or in your deep view. Okay, so now in this way, as you can see, if it is in this particular menu, a tick mark is placed in front of this 1HHO. This indicate that this 1HHO model is now being selected. Now if you click over here, the tick mark would be transferred to the next layer, indicating that the next layer would be selected. So whatever is selected, it is usually represented by this red color in your layer infos window. This 1HHO is check marked over here, that means it is selected. Okay, so well, say for example, if you click on this 3HHB over here, previously there was 1HHO. Now after selecting it, it has changed to 3HHB, and correspondingly over here 3HHB becomes red now. So whatever is the current layer that has been selected, well, it is being on display over here, as well as corresponding layer in your layer infos would be shown in red, indicating that it has been selected now. Okay. Moreover, you can also control what is being selected, or you can also control the activity. You can also control the visibility of the different models in your in your SPDB when there are two or more layers that are loaded. Okay, so you can control the visibility by using this visibility check marks over here, as per your preferences. Okay, so now, well, again, let us now again click on this control panel to activate it. Okay, so now I am pressing tab button on my keyboard. Okay, now let us see what happens when I press this tab button on and what and how it affects the selection in the deep view. Okay, so if I press tab, you know, the selection of layer is somehow changed in the in your control panel. If I again press tab, I mean, in this way you can kind of change the current layer using this tab button on your keyboard. And when I repeatedly press this tab, you can also see that the selection you can toggle the selection between the layers in your layer infos windows as well. Okay, so now I think you have noticed the effect on the file list menu at the top of this control panel. Okay, each time you press tab, deep view make changes into the active layer. So each time you press tab, the active layer would change. Okay, if more than two models are loaded, then deep view would cycle through them. Well, say for example, now we have loaded only two models, and when we have pressed tab, it would select, or you can say it would make the second layer active. If you again press tab, it would make third layer active. If you again press tab, it would make fourth layer active, and it would in this way go on cycling with selecting what layer would remain active in your selection. Okay, so this is how you can control as to what layer is to be selected by just simply pressing the tab button on your keyboard. Okay, uh, so another important feature is what we call it as control tab feature. Okay, so now what I am doing is that I am holding down this, press your control key on the keyboard and hold it down, and while you keep the control key pressed, then press tab repeatedly. Do you see what happens? There is change in visibility as well as selection of the two layers that you have loaded. Okay, so now this is also called as the blinking effect. Okay, so now you might have noticed that when you press this control and keeping that control button pressed on keyboard and repeatedly press the tab button on your keyboard, So this is called as blinking. Okay, and once you blink, you know, eventually the visibility and selection of your of different layer in your SPDB would change. Okay, so try it for multiple times, you would get hold of it, okay, of this task. Okay, so in this way, if you use this control tab option, successive layers can be made active and visible. Well, now let us make one HHO active and visible. Okay, so just make sure that one HHO is visible as well as it is active. It is active, why? Because it has been colored in red color over here. Okay, now let us color this active layer. Well, let us color by secondary structure. If we color by secondary structure, now you can see that it has been colored by the model has been colored by secondary structure. Okay, so now if you uh, blink, or you can say if you use the control tab, okay, now blinking would confirm that your color by secondary structure command has only affected the active layer. Okay, why? Because another layer that was not selected at that time, it is still colored by layer, and the one that was active, it has been colored by secondary structure. Okay, so what do this thing demonstrate? This thing demonstrate that unless you specify otherwise, most menu commands would affect only on the active layer. Okay, so if you want to work on some another layer through this menu command over here, you would have to make the subsequent layer or the respective layer active. Okay, so now there is another way around to handle with this situation. So now what you can do is that you can hold down the shift key and then pull any of the menu. Okay, well, say for example, now I am holding the shift key, and then I would go to this color menu, and I would color it by B factor. Now you can see that the model that was selected has been colored by B factor, and if I again blink, the another model is also colored by B factor. So what do this indicate? This indicate, you can notice that with well, say for example, with menu commands, the shift button extend whatever action you have taken to all the layers. For any key to have the effect on the menu command, you must press the key before pulling down any of the menu as such. Okay, so initially when we color it by secondary structure, only one layer was colored. Okay, then what we did, we press the shift button and then selected any of the menu for coloring. Okay, then it affected both the layer. So that is how that is what I want to tell, is that if you want some action to be done on both the layers, then you should be using this shift command before you pull out any of the menu from this main window. Okay, so this is one of the important feature. Okay, so now let us color by layer so that both the models have been colored properly. Okay, well, now this action coloring by layer will restore different colors to the two models. Okay, now let us blink to make 3 HHB an active layer. Well, so for time being 1 HHO is active, so let us blink it and make it 3 HHB as the active layer. Okay, now what we need to do is that we need to scroll down at the end of chain B. So this is chain A and this is chain B, as you can see. and we need to scroll down to the end of this chain B. Okay, and when you reach at the end of this chain B, you are supposed to select this heme from chain B, heme 1 from chain B, and press an enter in on your keyboard. That would, show only the heme. So what you see is the heme from the chain B of your hemoglobin. Okay, now we would switch on to 3HHO. Okay, so it is still not visible. What you can do, from layer info window, you can restore its visibility. Okay, then one HHO layer is active, you can scroll down to the end. Okay, and then select heme 1 from chain B. Okay, and again hit enter on your keyboard. Okay, so now you see that the two hemes from the respective chain B of oxy state and deoxy state are now on display over here. Okay, well, now let us zoom center it. Okay, so that it becomes bigger and we can visualize it properly. Okay, so what you see now is that you have got two beta chain heme groups colored in yellow and blue. Okay, so now the long bent line that you see over here, I'm talking about this one. The long bent line that you see from the center of the yellow heme, that represent the oxygen molecule of oxyhemoglobin. Okay, so now let us rotate these hemes properly so that we can see their faces. So let us call it as the faces of the heme molecule. Okay, so now what we need to do is that we need to switch off the movement of 1HHO. So if you let go, or if you deselect this visualization mark in front of this 1HHO from this move column, that would indicate that you have switched off the movement of 1HHO. Okay, this is what it means. Okay, switch off the movement of 1HHO by removing the check mark from the move column of the layer info window. Okay, now what we need to do is that we need to translate the blue heme to the left of the yellow heme. Okay, so now here is this translate button. We need to activate the translate button, and let us move on to the left hand side. Okay, you can again zoom center it, again move a little bit on left hand side, again zoom center it, again move a little bit, and again zoom center it. So now, well, you can kind of visualize the faces of both the hemes at the same time. Okay, this is done by translation. Well, let us come out of this translation function. Okay, and let us resume the movement of both the layers now. Okay, so by resuming this V mark over here, now you have kind of restored the movement of these both the layers. And from this translation, let us now use this rotation function to see if things are working properly. Yes, now they are both placed in the right orientation that we want. Okay, so now when they are side by side, I have kind of restored the movement of both the heme groups. Okay, so now let us try to superimpose these two hemes, and superimposing these two hemes would eventually mean that we are also superimposing the protein molecules in which those hemes are present. Okay, and now in order to superimpose, there is this button over here. Okay, so this button is labeled with these three red dots and three green dots and a curved arrow. This is what you need to use for superimposition. Okay, so now if you click over here, okay, uh, after clicking over here, that would indicate that this function is active. Okay, now this function is controlled well now the function controlled by this button allows you to detect to select or to pick up three corresponding atoms from the two corresponding layers. Okay, so what do this function says? Now it is kind of prompting you to pick up the corresponding atoms from the two layers, okay, from both the models, and then after you pick up the three model, it would superimpose the two layers appropriately. Okay, so now what you are supposed to do is that you are supposed to pick up the corresponding atom. Okay, so if you pick up this atom first, then the corresponding atom for this atom in the next layer would be this atom. Okay, so that would mean that you are superimposing this atom over this atom. So in this way you are supposed to select any three atom so that you can encompass the entire structure as such. Okay, so let us first select this atom. Okay, now it is prompting you to pick the corresponding atom to this atom in the model to move. So this is the corresponding atom to the first atom you have picked over here. Now it is asking you to select the second atom. Well, let us use this one, second atom, and the second atom, corresponding second atom in the model to move is over here. Now it is asking to select the third model or select the third atom. Well, let us select this one, and its corresponding atom in the second model is this one. So once you do this, now you can see that the two heme groups are superimposed upon each other. Okay, now again let us zoom center it. Once you have superimposed it properly, now you can see that it has been well superimposed, right? Okay, now what we will do is that we would again go to select, okay, and then use these neighbors of selected residues. Okay, so use this neighbors of selected residue dialog to add to view all the groups. We would use this add to view all the groups that are present in the vicinity of 4 Armstrong of the selected hymns in both the layers. Okay, so we would add to the view that are present in the vicinity of 4 Armstrong of this one HHO. Click OK. You have added a few molecule. Okay, now let us make this 3 HHB active. Okay, and do the same thing by going to select neighbors of selected residue, add to the view the groups that are within 4 Armstrong unit vicinity of the 3 HHB. Okay, so now let us make this 3 HHB layer active, and we have repeated the same procedure, and again press this zoom center. Okay, now let us select the visible group. Select the visible, go to the select menu and select, do you see where is visible groups? Okay, so if you select, if you use this command, go to select and select visible groups. So whatever groups that are shown over here, that would be, selected. Okay, and since the HHB is active, only the groups from from this the active layer would be selected. Okay, and then next thing I would do is that I would color it by root mean square. Okay, then I would make this 3 HHB active, and then I would color it by CPK. Okay, now the view is ready for what I want to show you. Okay, let us now analyze how things would change when oxygen goes and binds to your hemoglobin. Okay, okay, so what do you see now in CPK, or in CPK color representation, is the heme region of oxyhemoglobin, including the O2 molecule. I have colored it by CPK so that I can show that it is that oxygen is colored in red. Okay, oxygen molecule, and this oxygen molecule is bound to your prosthetic group heme. Okay, now in the shade of blue and green is the corresponding region of deoxyhemoglobin. Okay, so what you see in blue shade, the heme that is present in blue shade is the deoxy heme as such. Okay, to the one where oxygen is not attached. Okay, now the hemes are superimposed, so the difference in position of other group reflect changes in their position relative to the heme upon binding O2 or binding the oxygen group. Okay, so groups in deoxyhemoglobin are colored according to how far they lie from the corresponding groups in oxyhemoglobin. Okay, so now if they superimpose exactly, then they would be colored in the shade of blue, with colors farther up the visible spectrum are assigned for greater distances from the corresponding atom in the other layer. So this is called as root mean square coloring scheme, because deep view calculate the root mean square distance between corresponding backbone atoms to arrive at the color assignment of this group. So in short, what I want to say over here is that we have colored our superimposition as per the root mean square deviation. So, well, say in simpler words, if the two atoms are properly superimposed, or you can say if they are superimposed well, if the distance between the two atoms is less, then they are colored in shade of blue, and as the distance after superimposition increases, well, the shade of red would be used. Okay, now with this view, you can see that when oxygen bind to hemoglobin, okay, when this oxygen bind to hemoglobin, one of the proximal histidine residue, that is histidine 92, okay, let me go to select and select this visible group, and let me label it. Let me see where is this histidine 92. Okay, over here we have got this histidine 92. Okay, so now this histidine 92 moves closer to the iron atom at the center of heme. Okay, well, now let us compare it. Okay, let us use this control tab button and focus on this heme histidine 92. Okay, now do you see that when the oxygen, this is your histidine 92, when the oxygen binds, this histidine comes in closer vicinity to heme molecule. You see, it is located far away, and when you blink, it comes towards the towards your heme molecule. Okay, do you see now clearly? Focus over here. This is histidine 92. Okay, so oxygen binding changes the conformation of histidine to come to the close vicinity of heme group. Okay, so what happens that binding of oxygen to heme iron reduces the diameters and allow this histidine 92 to move into the plane of heme. Okay, so you should also notice that the iron is out of plane and the heme is cup shaped in deoxyhemoglobin, but when the oxygen binds, the heme becomes flat. Well, now do you see that this heme is cup shaped when oxygen is not bind, and it would become flat when oxygen binds to it. Okay, when oxygen binds, it is flat. When oxygen is unbound, it is in cup shaped. Okay, do you see this? Focus over here. Okay, so in this way, the heme also changes its conformation when the oxygen binds. Okay, similar is the case with the distal histidine 63. Okay, also check on histidine 63. Okay, now histidine 63 also changes in its conformation when oxygen binds to your heme. So this is oxygen, and focus on this histidine 63 now. Okay, so it changes its conformation, or it changes its position with respect to the heme group. Okay, well, now few more things can interesting things can also be, you know, uh, inferred from this thing. So for that you would need to compute the hydrogen bonds. Let us go to tools and compute this hydrogen bond. Okay, again blink it to make another layer active. Okay, and well, let us label the selected residue over here as well, and then again go to tools and compute hydrogen bonds. Now you can see that hydrogen bonding pattern is also different. Okay, so now when the oxygen is bound to your heme group in oxy state of hemoglobin, you know, histidine 92 no longer forms hydrogen bond with heme, but the moment oxygen is given up from this hemoglobin, there is change in conformation. It would become cup shape and it would form hydrogen bonds with this histidine 96. Do you see? Okay, similar is the case of hydrogen bond with histidine 63. Okay, when it is present in its oxidized state, or you can say in oxygen bound state, okay, this oxygen from histidine forms a hydrogen bond with histidine 63, and the oxygen, when the oxygen is removed, the histidine 63 goes away from the from its location, and the hydrogen bond is removed. Okay, so now I have told you that these are the different conformational changes that happens in the positioning of some important amino acid residues that are present around your heme group in your hemoglobin when oxygen binds and unbinds. So in this way, every time you hold down the control and press tab, that is when I say that when you are blinking, each time you press tab, one layers become invisible and another layer becomes visible. So you can switch back and forth. We call it as blinking between the views of oxyhemoglobin and deoxyhemoglobin. It's just like watching the hemoglobin breathe. Okay, oxygen bound, oxygen unbound, oxygen bound, and oxygen unbound. So well, now I have kind of demonstrated you as to what happens to the position of histidine 92 and histidine 63 when oxygen binds. What is the difference in hydrogen bonding when oxygen binds and when oxygen leaves your heme group? Okay, so now for your assignment, you are supposed to figure out at least 3 more conformational changes that happens when oxygen binds and when oxygen unbinds from the heme group as such. Okay, so you can take screenshot of this thing and focus on these residues to show that this is what exactly differs in oxygen state, and this is what exactly differs when your hemoglobin is in deoxy state. Okay, so you can prepare a kind of a word file, and then you can explain, take screenshot of this and explain as to what are the changes that you observe when oxygen binds to the heme group and when it leaves from that heme group. Okay, so this is all I have got for you guys for this presentation as well. I hope you are enjoying this structural analysis stuff. Okay, so thank you very much. See you guys in our next practical video.